Hi, we're Team Dermo, a multidisciplinary senior design team in the Kay Gleason College of Engineering. I would like to introduce our team, starting with Andrew Molino, our mechanical engineer, Nicholas Gonzalez and Yu Tan, our computer engineers, and myself, Ziggy Jaroniski, our electrical engineer. We're working with our clients, Dr. Carl Hirschman and Professor Stephanie Bolster, to design a system that uses optical interference to make in-situ film thickness measurements during a wet chemical dissolution process. This system is called a development rate monitor. The key goals of this project are to have an automated device that reduces overall noise, has chemical-safe application, is easy to disassemble and clean. Our stakeholders are interested in a cost-effective solution that captures and displays real-time data, all with simple controls. Our team expects to deliver an automated developmental rate monitor system that both agitates the chemicals being used and measures the results of the dissolution process. What our team's project does was based on an old system the Micro-E staff had many years in the past, and many subsystems of that were changed during our design process. The visual design of our device is heavily based on how a microscope would look, having optical equipment above the work surface. The work surface, in this case, is designed to be a constantly spinning plate. There is two reasons for this. The first reason is that the spinning would constantly agitate the chemical solution, not allowing unwanted crystallization. The second reason is that there only needs to be one stationary optical system for reading in multiple data points. The work surface is designed to house a standard 6-inch wafer, and this is designed for the surface of the exposed photoresist in set patterns. We are using a laser and line scan camera to collect the data in real time, to create real-time graphs as well as separate the data automatically afterwards into multiple graphs for further analysis. One of our major challenges was meeting one of our custom requirements that became difficult due to one of our design choices. We had a goal for a certain sampling rate of data, which was expectedly hindered by the rotating nature of our design. It was not out of left field, but it was more severe than we expected. The centrifugal forces caused a dry spot to form in the center of our test surface at the necessary higher speeds. With our developer pooling in the edges of our circular wafer due to this constant rotational speed, we introduced one solution, but that created new risks that realized themselves in our early testing. Our expected results are that the data we could read in with our system of the silicon wafer with exposed photoresist being chemically affected by the developer poured in while our motor is spinning the wafer at a constant speed. This data allows a 50mm diameter exposure ring to be tested over a set time period with separable continuous intensity graphs, giving microelectronic engineering students real data to be analyzed in a lab setting. We would like to thank our clients, Dr. Carl Hirschman and Professor Stephanie Bolster, as well as our guide, Jerry Adamski, and the subject matter experts, Gary Hodenius and Dr. Cormier, as well as our EMEE co-op student, Soren Schlatter, for helping us as well. We would also like to thank the IEEE Joint Chapter Meeting for allowing us to present our project, and with awarding our team for outstanding innovation and research. Please visit us in Engineering Hall on the second floor to look at our device in person. Visit our project website linked on this page to see more about how our project turned out. Thank you.